What problem does sharpness-aware minimization, SAM, aim to solve in deep networks?
Sharpness-Aware Minimization, SAM, aims to solve the problem of improving the generalization of deep networks by regularizing the sharpness of the loss landscape. SAM focuses on finding a flat minimum of the training objective by minimizing an objective function that seeks a solution where the loss does not fluctuate dramatically with any adversarial weight perturbation. SAM explicitly weights the gradient contribution of low loss points, particularly in the presence of mislabeled examples, to slow down the rate at which noisy examples are learned compared to clean examples. SAM's main goal is to achieve higher clean training before overfitting to noise, leading to higher test accuracy by prioritizing fitting more clean training data. Additionally, SAM is designed to be more robust to label noise than traditional optimizers like stochastic gradient descent, SGD, especially in the presence of random label noise, by improving early stopping test accuracy through its unique perturbation mechanisms on the logit scale and network Jacobian terms.
How does the 1SAM version of SAM differ from the naive SAM update, and why is it more robust to label noise?
The 1SAM version of SAM differs from the naive SAM update in that it applies the adversarial perturbation epsilon to each example in the minibatch individually, rather than computing a single epsilon for the entire minibatch. This individual perturbation for each example allows 1SAM to prioritize fitting more clean training data before overfitting to noise, leading to higher test accuracy. The key difference lies in how 1SAM handles the perturbation step, focusing on each sample separately, which results in a more effective regularization of the training process. This individualized perturbation scheme helps weight the gradients of low loss points, particularly clean examples, by adjusting the logit scale term based on the norm of the data point. This preferential weighting of low loss points allows 1SAM to maintain a higher contribution from clean examples in the gradient update during early training epochs, leading to improved robustness to label noise compared to the naive SAM update.
Can you explain the key conclusions drawn from the analysis of SAM's perturbation on the logit scale and network Jacobian terms in improving early stopping test accuracy?
The key conclusions drawn from the analysis of SAM's perturbation on the logit scale and network Jacobian terms in improving early stopping test accuracy are as follows. 1. In linear models, SAM's perturbation on the logit scale term results in preferentially weighting the gradients of low loss points, allowing clean examples to dominate the gradient update for longer periods during training. This prioritization of fitting clean training data before overfitting to noise leads to higher test accuracy. 2. The perturbation on the logit scale term in SAM acts as a gradient reweighting scheme, where low loss points are more affected by the upweighting compared to high loss points. This mechanism ensures that clean points are more heavily emphasized in the optimization process. 3. In deep neural networks, while the logit scale component of SAM does induce a similar effect of explicitly weighting the gradients of low-loss examples, the main contributor to SAM's robustness is found to be the perturbation on the network Jacobian term. 4. Specifically, applying the perturbation to the Jacobian term in SAM, JSAM, recovers most of SAM's gains in deep networks, while focusing solely on the logit scale term, LSAM, does not yield significant improvements in early stopping test accuracy. 5. The regularization effect of SAM on the Jacobian term in deep networks helps in maintaining the norm of the intermediate activations and last layer weights, contributing to improved generalization and robustness under label noise. 6. By explicitly reweighting the gradients of low loss points and regularizing the network Jacobian, SAM achieves higher early stopping test accuracy by emphasizing the importance of fitting clean training data effectively before being influenced by noisy examples. 7. The analysis suggests that SAM's benefits in improving early stopping test accuracy do not solely rely on the explicit reweighting of the logit scale, but rather on the regularization of the network Jacobian, which plays a crucial role in enhancing the model's robustness to label noise in deep neural networks.
What experimental investigation was conducted to compare the performance of full batch gradient descent and SAM on toy Gaussian data with label noise?
The experimental investigation conducted to compare the performance of full batch gradient descent and SAM on toy Gaussian data with label noise involved training linear models over a toy Gaussian data distribution where the first dimension contained the true signal, while the remaining dimensions contained uncorrelated Gaussian noise. Training data points were sampled from this distribution with a certain percentage of random label noise. The test data was assumed to have no mislabeled examples. The study involved running a grid search for the magnitude of the adversarial weight perturbation used in SAM and observing the early stopping test accuracy as it monotonically increased with the perturbation magnitude. Additionally, the ratio of the average sample-wise gradient norm of clean examples versus noisy examples along training was analyzed, showing that this ratio decayed slower with larger perturbation magnitudes in SAM. This indicated that clean examples dominated the gradient update for a longer duration, leading to higher test accuracy by fitting more clean training data before overfitting to noise.
How is the explicit reweighting of low loss points by SAM's logit scale term different from the effect of perturbing the Jacobian term in SAM for deep neural networks?
The explicit reweighting of low loss points by SAM's logit scale term differs from the effect of perturbing the Jacobian term in SAM for deep neural networks in the following ways. 1. In deep neural networks, the logit scale term of SAM explicitly up-weights the gradients of low-loss examples, prioritizing fitting clean training data before overfitting to noise. This effect is visible in both linear models and neural networks, where clean examples dominate the gradient update for longer periods in the early training epochs. 2. On the other hand, perturbing the Jacobian term in SAM, specifically in JSAM, is the main contributor to SAM's improved robustness in deep networks. Applying the perturbation to the Jacobian term recovers most of SAM's gains, while focusing solely on the logit scale term, as in LSAM, does not yield significant performance improvements over SGD. 3. The Jacobian term in SAM for deep neural networks regularizes the norm of intermediate activations and last layer weights, leading to a more stable optimization process. This regularization mimics the effect of SAM's perturbation on the network Jacobian, resulting in improved performance and robustness under label noise. 4. Empirical results show that while the logit scale term of SAM does induce some effect of explicitly upweighting low-loss examples in deep networks, the main mechanism for SAM's label noise robustness lies in perturbing the Jacobian term, which regulates the network's behavior and contributes significantly to SAM's performance gains. 5. Overall, while the logit scale term of SAM plays a role in reweighting gradients in both linear models and deep neural networks, the perturbation of the Jacobian term is the primary driver of SAM's robustness and improved performance in deep networks, showcasing a different mechanism that originates in SAM's Jacobian term for achieving label noise robustness.
What proposition is presented regarding the regularization effect of JSAM on a two-layer deep linear network, and how does it relate to the performance gains observed with SAM?
The proposition presented regarding the regularization effect of JSAM on a two-layer deep linear network is that JSAM regularizes the norm of the intermediate activations and last layer weights. This proposition relates to the performance gains observed with SAM by showing that the regularization effect of JSAM on the network's Jacobian term plays a crucial role in improving the robustness of SAM in deep networks. Specifically, by perturbing the Jacobian term in JSAM, the update decomposes into SGD with L_2 regularization on the final layer weights and intermediate activations. This regularization helps in keeping the loss of correctly fit points high, by constraining the magnitude of the network output, which in turn leads to improved generalization and performance gains, especially under heavy label noise conditions. The regularization effect of JSAM on the Jacobian term is highlighted as a key mechanism that contributes significantly to SAM's robustness in deep networks, surpassing the impact of explicit reweighting schemes like LSAM.